Alright guys, we're going to show you how to crush a can. The ingredients you're going to need, or the materials you're going to need, are something heavy that you can seal a can with. We're going to be using a crowbar. A small paint can. Some duct tape to seal the can off. We've put a little hole in the top of it. And a pair of tongs to move the can whenever it's hot. And a dry ice and alcohol bath so that we can cool the can down rapidly.
Alright, next we're going to take our small paint can. Then we're going to add some water to the can and the lid and seal it up. And then we're going to take a nail and use the hammer to put a small hole in the top of it. Now this hole is going to allow some steam to escape so the can doesn't blow up or anything like that. And it'll also indicate whenever it's ready to be pulled off the heat. Once it's pulled off the heat, you're going to use a small piece of duct tape to seal the hole so that now we have an airtight seal.
Alright, for making the dry ice bath, what you're going to need is, you're going to need your dry ice. You're going to need some gloves to handle the dry ice. Something to break it up, like a crowbar, like a hammer or something. And you're going to need like a pot or a bowl to put everything in. And you're going to need your rubbing alcohol to get this thing nice and cool. So we're going to start out with our little pot here. And we're going to dump the rubbing alcohol in here. That should be enough. And we're going to put our gloves on here. Alright, and now we're going to break up the dry ice and get it into little pieces. Oh, wow. One more. That should be good. Alright, now we're going to take the little pieces and just kind of drop them in. Let's see. Alright, now we're going to perform the experiment here. We got some water heating up here in this pan just a little bit. What we're going to do, we're just going to place this little can right in here. Get that heating up. We might need these. Let's see here. Need that. This little spoon to scoop some water in here. Might as well do it real quick. Just a tad. Oop. Alrighty. Let's just let that heat up for a little bit, get it nice and steaming. You know, you see a little bit of steam coming out here. So what this is doing is it's heating up the can, getting a nice little hot source here, heating up the water in there to turn it into steam. It's going to create like a vacuum, and the change in pressure is going to slowly crush the can. I think it's ready.
And that is how you crush a can with science.
So now we're going to go ahead and show you what is actually happening in this thermodynamics experiment. For any thermodynamic problem, first you have to make a diagram, and so we have one here. We have state 1, which is the actual can before the crushing starts, but after the heated liquid or steam is inside. So you see the steam has a certain pressure, temperature, mass, volume, density, etc. inside that state, and then that would be a different temperature and pressure of the surrounding area. And because the heat goes out and the work goes towards the bounds of the state, you will get the crush in state 2, which will have a different pressure, temperature. The mass will stay constant. The volume will change because the can has actually crushed, and the density will change because it will be going from a gas to a liquid state. So now we have the regular standard energy balance. So we have the Qin plus work in plus energy in minus Q out plus work out plus energy out equals a change in energy. So first we can get rid of the Qin because there is no actual heat going into our state 1 to crush the can. Then we can get rid of the energy in because there's no mass transfer in or out of our closed system. Then our work out can be because there's no work going out of our system, only work going in. And then the energy out, once again, there's no mass exchanging, so there's no energy out. And then so that gives us a nice equation once we bring everything down with just the work in, the heat out equals a change in energy. All right, so we can rewrite the equation like this. That's the work in is also can be written as the integral of the pressure to the volume, and that we minus the heat out net, because you can technically say there's probably heat going in, but most of the heat is going to be exiting, so it will cancel out the heat going in because heat goes from a hot state to a cold state, and since the heat is inside of our can and our ice bath would be the cold area, it would be exiting, and that would equal to the mass times the CB onto T2 minus T1, where T2 would be the temperature after in state 2 minus the temperature at state 1. And now we have the entropy balance, which would help with our second law of thermodynamics, and that would just be the Qn over the temperature bounds plus the mass in times the entropy in minus Q out over TB plus mass out, entropy out, plus the entropy generated equals the change in entropy. Alright, so we can also get rid of the Qn because once again we have no Q going in, like we have no heat going into our system. Once again, there's no mass coming into our system or exiting since it's a closed system. The mass out can also be eliminated, and that will give us, with a little bit of algebra, the entropy generated equals the change in entropy minus the Q out over the temperature bound, and that can also be written as the entropy generated equals the CP ln 2 over 1, which is the same T2 over T1, which is the same T2 of state 2 and T1 of state 1, minus R of gas ln of P2 over P1, which is the pressure inside of our state 2, which would be less than our state 1 because of the state 1 being a higher states of movement, minus the Q out over the temperature bound.
Now we'll talk about some real-world applications of our experiment. In our experiment, we used steam to generate a vacuum to reshape the metal can. What we did is similar to vacuum forming. Vacuum forming is the use of applying a vacuum onto a material to shape it against a mold. Some of the materials that can be used include plastic, carbon fiber, fiberglass, and even metal. Here's an example of a vacuum forming machine. In the main bed area is where the mold of the desired shape goes. The material being formed is placed at the top and heated to make it malleable. The top part is closed over the mold, and the vacuum pump at the bottom is turned on to draw a seal on the material and mold. Once the material cools, you'll have fully taken the shape of the mold. Here's an example of vacuum forming plastic. Here's another example, this time with metal. This process is also scalable. The vacuum generated can be applied to even larger containers or structures. It's powerful enough to crush a full-size tanker car.